Let us welcome today's speaker, Arnab Saha. He is from CALCUTTA University. Arnab is like, he is back to his domain. He did PhD from SMS in base school. He graduated year 2011, and after that he went to Max Planck Dresden as a postdoc and spent 3 years till 2014. And after that he went to Düsseldorf and stayed a couple of years till 2016. And then from 2016 to 2020, he member the University of Tech. And in 2020, he shifted to Calcutta and he is there. His main interest is and broad sense. Today, he will tell us something about more of non-equipment mechanics. So, I welcome.
Thank you. It's always good to be back. Thank you. So today I will talk on self-organization. So content in the slide also.
Yes, you can. You can send it.
So the basic content of my talk will be in parts. First, I will start with examples. So in the talk, you can just ask for students or also everyone. There is no need to finish. So first, I will start with some example, and particularly the active systems. What I mean with active systems and how. So particularly stress on the examples where we part of the system is external. Why we part of, how we part of, then or people part of, then those things I will discuss first, and then I will come to some model simulate, calculate something else. Then finally we'll see the self-organization in those blocks. We'll see that how they self-organize, and finally we will come to the model. Then, so this is one example of active systems. This is what active is. What is happening here? So this is this. So this round shape thing is a block of that fish. And what is happening here? This whole process, something happening in the process. The process is called body, which is a particular life stage, developmental stage of generation. This is embryo, and you see a multicellular layer. So these are all cells. Okay? So these layers, so this layer is called enveloping layer. It is covering up the whole block. And why it is covering two things? One, there is something called cell division is happening in this hole. So this is, and then there is a bright ring forming on the way. Right, that was this bright ring is then actin network, and on top of that, the myosin proteins are working, so they form some contractility. And due to this contractility, it pulls and pulls in this forward. So basically, this animal we all have actually these three layers across the CALCUTTA and mesoderm. So here, this particular layer will turn into the mesoderm, the full. So this is one stage of. So what we do here, or people do, what is the property of this bright ring? This is self-contracted layer of fluid. What is its contracting? What is its viscosity? What is the friction that is facing on the top of the box? Those things one can part in the system. How we part? So this is the way of perturbation. So this you see a line here, red line. So that is where you cut along the line the laser. Then you see how the flow around the layer, and you have a theory, you build up a theory. That theory contains those parameters like elasticity, viscosity, contractility. Then you match the flow surrounding the cut, and then you get those parameters. Those parameters are important in that because by that way you can predict whether so one example one is that whether this full blown body will be uh, perfect or will be formed or not. So those information is hidden in the parameter values. That's why we are there. So this thing, so this is the experiment that. So here we actually have this active gel theory, and this is the model that we have computers, and then we can compare the theory and the experiments, and we get the parameters. For example, this tau A is the wound healing time. You see, this process is called wound healing. Uh, this this cut is here, and then it opens up, and then finally it heals. Right? This is this time scale. You can actually calculate here. Then this is the hydrodynamic length, the length scale of the flow. So this is the purpose to characterize the active fluid. This is the purpose for perturbing. So next example. So one is very popular active system now is called active colloids. So the colloids which has due to some chemistry on the surface, they run, and as they run, they form clusters or structures which is not possible to happen in passive colloids. Now, with these active colloids, also people do a lot of experiments to control them. They perturb the active clusters, active colloidal clusters, and by perturbing them, they actually it's possible to guide the cluster, control the dynamics of the whole cluster. So here, this is the cluster of active magnetic active colloids, and they can tune their dynamics can be tuned by external magnetic field. The structure also can be tuned and very precisely. So this is one of the examples that they claim this field will be. Now you can think of now we are slowly coming to the model blocks or something. So you can think of this boundary as also a perturbation from external confinement. So here we took very common example of active models like jet models. So there are particles, they align, they move in a certain velocity with constant speed, and they also see their neighbors, take the average value of their velocity, and then they decide that whether they will go with the average or come and point something. Okay, so there is basically an alignment interaction between them, and if you put all those talking particles in a circular boundary, you will immediately see there is a spherical symmetry. So you will see that more in some places these particles go and stack, like, not stack, but they are accumulating in a particular region with the spherical symmetry of the trap. Then there are many other examples also. For example, this here is from Bolgar's book. There they put the active dominant particles, not the reject one. They don't have any aligning interaction, but they can self-propel. These are also colloids. They are self-propelling. They have some kind of impulse interactions between them as well, and they form something like pump. Basically, if you put them in a harmonic trap, they come close to each other, not at the middle, not at the middle position, somewhere else, and they form the pump. They form the pump. Similar thing also seen by Ronojoy a few years back, and they are also they do lattice Boltzmann kind of simulation. And here, this is much bigger system, not colloids. There are something called cobots or something, moving robots. So they keep these robots in a circular track, and all the robots go to the boundary, and they. And here is another example from that they also have a hydrogen interaction between the active particles and they form crystals close to the boundary. So then this is a real life example of which is anyway part out because of wind. Right? So this is beehive and there is wind flow from any direction. They can be force, they can be shear, they can be, but the point is this is quite stable. Of course, if it's storm or something, then it's gone. But normal wind, normal moderate shear, they're quite stable. And these kind of controlled experiments on this thing is done by Mahadevan's group. So they have their so this is beehive formed in the lab, and they have this shaker. So if you this, so they are quite stable with this horizontal shaking. For example, here, why they are stable because they can reconfigure themselves. So this structure changes, becomes flattened and becomes stable. But this thing can be done with the particle shape. So if you shake the beehive vertically, then eventually they are not stable. So why they are doing this? So the major point what I want to make here, the important thing is, of course, the active cluster also responds to some external perturbation. Passive thing also does. Right? There is elasticity and everything. If you pull a steel bar, show something like extension or something. But the point of difference is the reorganization. It's in the dynamics of the particles, individual particles, how they reorganize themselves and make themselves stable. That process is different, very, very different. We want to study that process. That is why we put some model clock here now. This is now so that here we have some experiment from Picard's group. 2015, they have some provider controllers. Okay. What they do, they are a colloidal particle, but they roll within the fluid. And as they roll, their hydrodynamics, the hydrodynamic interaction between the particles are such that they can align themselves.
No translation, only rotation.
Only rolling, not also rotation. It's like spinning. Okay. But this will eventually lead to translation and rotation because of hydrodynamics. Okay, so finally they will have everything: rotation, translation, rolling. But to take a single colloid in a fluid, we will need. So what will happen with this? Uh, so after a few transients, they put all these molars into a circular cavity. Now what will happen? You will see that they will all go to the bottom and they will rotate along the bottom. Here, this red one is the boundary. Now what we did, I think that we took this active particles, but instead of hydrodynamics, what we do, we given the project like alignment. Doing actual computing hydrodynamics is very difficult because it's 1/r. It's boundary interactions. No theory on definition. So now essentially what hydrodynamics does here is the implementation of alignment actions. So then we put this model by hand. Let me check alignment. Okay. You see that's very similar. So first I will come to the colors, what the colors mean. But first see the organization. So they all go to the boundary and they all rotate along the boundary. And these colors mean the local Versailles order. Means that these colors are close to here, so they are not really spatial order. But they all move the boundary and they go and they rotate along the boundary. So this is very similar to that. So basic message is like we have, if you have self-propulsion together with aligning interactions. You come from reject like algorithm, if you come from hydrodynamics, but somehow if you have alignment interaction, then you can expect similar.
But the sense of rotation, what decides this?
Spontaneous. So they go and
No, I'm saying that, like clockwise.
Yes, yes. In
That
some
is selected
spontaneously, but in some run you will get
Oh, I see.
clockwise. In some run,
Once it starts rotating in the direction,
then it
It,
follows
it follows.
because of this alignment.
Alignment.
But the initial thing is decided. Now the fun, okay, this is the model, basic model that we split. This is very like algebra equation. You have Stokes friction, you have passive forces. Passive force means you have the trap. The potential I have used is tan hyperbolic 1. It's a circular groove, you can say, and this is WC, passive function, repulsive interactions, and this is the active force, okay? And this is the Jacob action. So this is the neighbor, and we average over the neighbor direction. This is the random chosen theta, which I think. So this is basic model, very simple. Then what we do, is now we want to see the effect of power. So right hand, this one is the very same that I showed just one step back. So this thing is very sharp. That means this wall is very, the model, it means that this Q factor is very large. It's very sharp. And in this half, this Q factor I have shown out like smaller than so. So the wall becomes soft. So now we see how this effect, how this self-organization of these particles changes. What? So this one you already have seen that they go to the boundary. There is no spatial order, form a kind of layer, weighted layer. This you can see that okay, they are all divided the boundary, so it is weighted layer. But here this is something very different. Only the boundary changes, but here we see that therefore, first of all, there's a weighting duration transition from here to here. Because the cluster goes brown, the contact angle raises. This is the first stage. Second one is the order inside it. So we all have exciting system. So this color means that exciting order color, the local exciting order color. So locally they are triangular, they are forming triangular lines. So this is what happens. So this clear phase transition is there. So when it is hard, the boundary is hard, there is no order, but there's a weighted layer formed. And here, think about the soft. That means we're having a rounded cluster. So weighting transition already happened, and we have an order.
And this is true.
All the calculations I'll be doing here now. So naturally, the next question is what the phase diagram. So this is the phase diagram. So here is the steepness of the boundary S, and this actually is the plane. And you have the order region. You have the lower steepness, so it's soft boundary. You have this ordered region, and there's the liquid-like order, and there's the gas-like order. This is the phase diagram. So the next question will be the kinetics. So how these particles are here. So that is the basic question. We do see all these phases even in the passage, right? But how the organization does of the part. So remember there is step transitions. First is the kind of weighting deviating condition. We say it is fragmentation. Where so start from here. So here, so this is a very sharp bound. Okay? And what we so this part is zoomed here, and the color is the potential that they are facing. These particles are facing. Now, when the boundary is very sharp, the particles close to the boundary, they are facing the boundary. So here the potential is very large. The interface between the trap and the cluster is also smooth, and all the particles below, they are not facing it. Once you make softer and softer, so you draw a length scale there. That means that your particles behind this layer are also facing the potential. Facing the potential means they are repelled from the trap. Now, due to activity, what happens? Particles try to go towards the trap, and at the same time, they are also facing repulsion from the trap. So one is going up towards the trap, say, and the other force is going down. So there is a competition between these two, and therefore there is instability. Okay? So this is the instability happening. So we see the ripple formation. So the smooth interface becomes brittle. And once you even make the boundaries softer and softer, finally you or this interface here form fragmented clusters. So this is the first step. Now still they are not very much ordered. Now comes the rolling, which makes the fragmented cluster ordered. So why they roll? Because see, uh, so there are two forces. One is going down towards the center, say due to the trap repulsion. The other force is active force, which is towards the trap. So there is a force couple formed within the fragmented cluster. Therefore, it generates torque. Therefore, those clusters, fragmented clusters, started to roll. And while rolling, it's a snowball effect that all the particles of the fragmented cluster, they face the potential. Therefore, they can become compact. Therefore, the order can be generated. Is it clear to all the students, the mechanism? So this is what exactly we quantify. That this is the 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 mechanism I just mentioned will have most impact in the radial component of the velocity of the particle, right? Because so this is the distribution of the radial component of the velocity of the
That's what like do the steady state.
steady state. This is a steady state. So this red one is where this thing forms. It's liquid like that. So there is not much standard deviation. Because no, so if you have rolling, that means you have some radial velocity in this direction and other is this direction. So there is much more deviation from the mean to be expected. That is here. This sigma here is much larger. This condition. So sigma here can tell you that what is happening. If it is small, then it is not rolling. If it is large, and rolling means rolling generates order. Is it clear? So that's what we will see also here. Um, here. So this is okay. All the particles they rotate and roll. So therefore, if there is rolling, then there is multiple frequencies. And when you have multiple frequencies, you have decided right? So this configuration will not show any miscellaneous figure because they don't roll, they only rotate. You'll see. So how we see this? We plot a typical trajectory of the particles, the red one. So you don't see any miscellaneous figure here, uh, just rolling clusters. But what happens here? If I plot the typical trajectory of the cluster here, you'll see a clear miscellaneous figure which will signify there are multiple frequencies. One frequency is associated with rotation, other frequency is associated with
So while rolling, the clusters actually fall.
yes, yes, they balance more. They actually become compact clusters. Therefore, they have repulsion WCF. Naturally, they form crystals. Exactly. See, this, I'm not sure.
Maybe factors are making clusters. High yields would get stick together
See, there is no, so
because you did not apply any attractive force anywhere.
see, they need form cluster, they need attractive force if you have passive particles. They are active particles. They are moving. Therefore, activity can generate an effective attraction. So this is again the distribution of scrolling frequencies, and so we can get an hand waving scaling kind of argument to check how this sigma VR, that is the signature, if it is
How do you quantify this rolling and rotation? So in case of rotation,
you go to the center of mass, then you can quantify this omega around the center of mass. That's the rolling frequency. And if you are in the cap center, which is the origin of the problem, then it's the origin anywhere, but I choose it in the cap center to get the frequency of.
in case of this rotating, there is no radial velocity.
Because it is trapped. Understanding rotation is much simpler. As it is trapped, all the particles are trapped, so they can go out and they go to stick to the boundary, they can move back and then they rotate.
But in case of rolling,
They are rotating and they are rolling also. Like an rigid body. There's a standard mechanics problem, right? You have a disc, it can roll and it can rotate both. So that is what happens in the solid in the exact. So now you can get a scaling with the hand waving kind of argument and the scaling arguments, that how this sigma VR, that is the standard deviation of the radial component of the velocity of every particles, they behave with the stiffness of the. So it seems like this thing shows that sigma VR goes as the stiffness to the power minus half of the cap, and this is the theory and get points are from the simulation. So this is the self-organization, and now we can do also a continuum hydrodynamic theory, get feelings that how the instability how we get the instability. For that, we can borrow the hydrodynamic equation for the object. So this is a couple tens of years back, maybe from Eric. And then you have to couple this dynamical equations, continuum equations, with another continuum equation for the density. And here also this W is there, this UV is there, and the right hand side is much passive, I would say. So this is passive diffusion, passive drift due to the potential, and then this J for the W. And so this is we can calculate it. So the diffusion is drag growth and drift is JWCA I borrowed from dynamical density function theory, and it is with some kind of arithmetic approximations and all. Then finally you can do a stability analysis with these equations around this state. So you have a smooth interface, okay, and how this interface can become unstable. So you add some small perturbation and see whether this perturbation flow or shrink. So we see that the radial component of the perturbation can go, which can give you the results. So this is the stability analysis, linear stability analysis. That much you can do, but the ordering, getting the ordering cluster, so the second instability, that is difficult to get from this linear stability. From there, you have to get a fragmented cluster. The profile itself around which you have to perturb is very difficult, so we can't do it actually, right? And so this part, up to this part, we can actually do. Now we switch to the third point, that how how information can flow within this confinement, within this confined flux. It's important because anytime anything can happen. For example, here there is a block, though it is unconfined, but there is a block of fish and the shark is coming to pick them up. So there are huge structural reorganization. But on top of that, they all it is very evident from the dynamics that they also transfer information to get away from the data. They all So, starting from the structural changes, the structure it is kind of intuitive to us that whether the structural change is very much correlated with the information within the problem. That's what we wanted to explore with the model from not of course with this theory. So then what we took our old friend on blocks know anything based on this happening. So now what we do are quenches. Quenching means what? That we start from here, this phase diagram. We are ordered clusters, okay? And then what we do, we suddenly quench the trap boundary. The Q of the trap will suddenly change. Then what happens? So this you can think of kind of a predator schema. Suddenly the structural change is happening. So this static order falls, the polar order falls, the structure changes, solid becomes liquid. But these are all mechanical structural changes. So this is what happens in the quench. Then we ask, actually, after doing this quenching experiment, we ask issues. What is how are the fogging particles informed about the quench? Maybe something happens with the boundary, right? The boundary becomes suddenly very hard. Then how the interfacial particles know? Like how the question is how the interfacial particle transform the information that the boundary becoming very hard, the particle come back, and how fast it is. Those are the questions that we want to ask. For that, we have to quantify first. Second, if the information goes, then how fast it is, how big, right? Scales of the program. This is second issue. Third is how the scale, the time scales or length scales of the flow information compares with the structural time scales. Those things. The first step is to quantify the information. For that, we have to take a measure from information theory. We borrow this. There are several, but this seems as logical because they so it is first of all very similar to mutual information, but it takes care about the history of the particles. Okay? Not only particle activity, but also the history. So what it okay. So first go to these figures, then we will come to the definition. So this is the my focal particle. Say, I am sitting on this this part, this part. Now each and every time point, this bird is getting information regarding orientation, regarding position, right? Of this part. Because at this t is equal to t1, say these are there each layer. Now this layer is horizontal here. Here. These are history. So these particles, these are the particles, these are the properties of history. So up to k is equal to 5, 1, 2, 3, 4, 5. 5-step history I am considering. In general, this definition is for any thing, like zeroth time also. But for the time being, I am taking 5-step history of this focal particle and 3-step history of the neighbor particles. Then we calculate the joint. This is the conditional probability distribution. So this is my ith particle, and this is the j, and j is the neighbor particles. Okay, and this is the ith also. So this is the conditional probability while considering I and j both in the past, and we are considering only I. Okay. So now, and this is the joint probability distribution. So basically, this distribution we have already this definition people have already used in fact in case of information channels. So you have a channel where some information is propagating from point A to point B. There are other channels we don't know them exactly, but what kind of influence the other channel faces or gives to the focal channel. So this is their that one.
So when you are considering a five-step history of your
Focal part.
should they not be dependent on the history of
Yes.
their
Oh,
neighbors
sure,
as
sure, sure. So that's why we also take into three steps, for example. So this can be independent. This K and L can be independent.
or
So
they can be dependent,
and they,
or
they can be dependent. And we don't know
because,
actually.
say you were just one step back.
Hmm.
So when you are one step backward, say that is your origin for that,
Mm,
and you are now looking at your neighbors.
mm.
So those neighbors
May not remain my neighbor in the second step,
yeah. Oh, okay.
right? The neighbor will change. That's why in general this K and L are independent. In general, but if you are very much correlated crop, then of course. So we lose our friends, right?
It's not Markovian.
No.
Yes, this definition itself is not one. So you can also think of, so this is your focal channel of information. Okay, that's what you are focusing on. And this is the neighbor channels. So what you finally, so this you can compute over given the talking particles. And you more importantly, what we did here, that we compute it locally. Locally means I have sitting on this particle and I am just concerned about my neighbors. Right? And then I get some information from my neighbors and I quantify it. This is called transfer entropy. Why I quantify it. And then what I do, I just paint these particles with here. So these are the color shows this transfer entropy. And the same plots painted by the transfer entropy, right? The information that gets from over the time. And we clearly see there is a shock-like movement from the boundary back here. When it collides with the boundary is hard, very hard now. So it collides with the boundary and get a shock. The information flows something like shock. But visually, we haven't measured it or quantified it so far. Now, I can ask a basic question: what is the length scale of this movement? What is the time scale of this movement? So this is so these are the snaps. We can clearly see that the length scale. So this is the information front moving from here to the end of it, and it is almost like a linear size of the front. So all the that means that all the particles of a moderate size block should know about the transition happening at the boundary. May not get the same time. At this time, these people will know only. But in the later time, when this flows throughout the process, by the time all the members are known about that. Something. The front size is close to the linear size of the front. That's what we see. It's all observation. Then what about the time scale? To determine the dynamics, that how the information front flows, moves, we compute the distribution of this entropy, transfer entropy over the particles, and this is before collision, before the point. This is during collision. This is after collision. So what we see here, a tail appears during the collision, and we can so that means the tail means what? Some particles, very few particles have large information, large value of transfer. Okay? So they form these tails. And how the tail goes, that will give me the information about the time space. So how information goes. So these tails, they are not there before collision. They disappear after collision, but they appear during the collision and decay. So these time scales, their dynamics will show us how fast the information.
Nearby the
Not always. Only boundary parts. So, for example, here they are also forming. They are also within the tails, but they are not close to the boundary. Initially, yes, but later, no. Here, and finally, they are the farthest particles from forming the tails. Yes. So this is the tail statistics. So we actually distribute we took the how many particles are there in the tail, and we plot them over time, and we saw that this increases, and this increase is ballistic. So it goes linear with time. So we can at least say that in this modern clock, the information goes linear in time. But okay, so these are all computation. Uh, but so far, what we have done is this, but very difficult to do analysis. Otherwise, what happens? It's difficult to get a feel that how information is going from one particle to another particle. So, there are two particle. We are searching something like that where we can compute two particle system, two active particle system, where we can actually see by calculating that one particle is giving this information to other. So that is in progress now. So far we can. This is the self-organization part that we have already discussed. That how we get the transition from liquid to ordered solid or exotic structures, tuning the boundary stiffness, and that leads us to the experiment, the quenching experiment for information flow or compute on the clock, and it shows that so the length scale of the flow uh, is linear size of the clock itself, and the information goes through the clock. That's
Okay, thank you, speaker. And then questions or any clarification? Yeah.
like alignment reflection. It's also propagation of information. Actually, their interactions. But if we take non-interacting particles, they don't. Uh, I don't expect they will transfer information from one to other. But these are even if you check like interactions or any kind of passive interactions, even there are information flows, right? So they are interactions. Via interactions, information flows. So, and this alignment is an interaction. It is not information. It is not information. There's some kind of any kind of interaction may happen. Maybe there is the particles, right? There happens to be here the big check light. There are many other kind of interactions possible, right? And given those interactions, you can compute information. That's so interaction is a mechanical. So like, there is no interaction, there is no flow of information. I think so. Yes. You have to interact, get some information.
So more questions?
Not a question. The one having showed that after being nearby to the boundary, the information is like if some particles the real is it somewhat similar to the dominant of the perturbation on the parts? And so they are already exactly what the consideration. But when some perturbation, it's kind of
Here it is similar, but the thing is, it depends.
don't have the
No, we don't have, but the okay, the particles doesn't have the memory, but the definition has, right? How we compute, that definition actually takes care about the. But it is an interesting question whether we have, if I have particles with memory, like non-Markovian dynamical process itself, then what will happen? Because we haven't computed. So we just have the Markovian process, but the definition itself contains the history of the particles. At least to some extent.
So yeah.
Yeah.
Okay.
F0 is a parameter, constant parameter in this model. So F0 we don't change. So F0 is independent of time, independent of space, fixed number. So it depends. So we change it, but changing it, we calculate the phase value. The F0 numbers we change it, but it's constant.
It changes like what is the like APP or RTP kind of error.
In the standard APP model, F0 is still a constant, but people work on something like space dependent speed or time dependent speed. There are different models on that, but we stick to the F0 equal to constant.
Small comment, like, so if the ballistic propagation of information, so is it a consequence of this propagation of antiparticles which are ballistic?
Actually, the propagation of the active particles are not ballistic. You see the long
Yeah,
time.
even microscopic.
Even microscopically, there are some active force, but there are noises. There are reject noise, there are thermal noise, like
But definitely the active force is winning. That's why you
active force winning, but is still if you take an individual particle, say I am not interested about the cluster. I take an individual clocking particle, the moving particle inside the group. Then you will see that over the time it will go all throughout the group. In that case, that we have checked. So it is so the memory, not memory, but I would say that activity means is to mean are in the ordered region or so, but it is not like that they are ballistic individually because of the confinement, because of the noises they have. Don't think they are ballistic.
so is there any universality kind of?
People have calculated for a single particle. That's for small time they are ballistic, but for large time, if you go to the large time, they are still at least in the case of remedies. No. I have seen a single particle.
That's true. But then,
Oh, information, no. I don't. So we just calculated it in this particular model, this particular phenomena, the information profiles. I don't know if I change the model itself. Say I don't have the alignment interactions. Then what happens?
even this, even if you just say increase the number of particles, so the cluster is
That
very
we have checked. That we have checked. So that is actually we did for different number of particles. So these are the 4 different boxes for 4 different size. So n is equal to 2000 here, 1500 here, 1000 here, 500 here. Yes. So at least for these things is there. Actually, this computation is quite heavy. So has to go into thousands of particles or millions of particles. It suggests where you have this confrontation with the boundary. So there is this thing, right? So here you have this boundary. The particle comes and here these particles visit the boundary, right? And from there you start the inflow of information. From there the tail begins. So that is why we characterizing the tail behavior. We get the time of the lifetime of the tail is the lifetime of the information. A boundary to
Yeah. Okay, no questions. Well, if not, I have 5 questions. First, the instability that we talked about, has it got anything to do like rally instability? Because rally stability also occurs in the interface.
We have actually thought about it and there is a similarity with the rally, but there is dissimilarity as well because in case of rally we have a specific direction. Here also we have but the specific direction is emerged somehow in this kind of thing. So it may happen that always it is not rally. In particular flocking stage, it may be the same similar thing at least, but not always. So, but it's similar. That is some cases.
Now, second question, even more like for the information transfer, do you really take an activity? Like if you have this passive particles, but
But
this is not
interacting, yes.
So this should also be
Actually, that is true because see, all we need is this.
I mean, this should be non-zero, right?
This should be non-zero.
So
Then
it
you
should
have.
be true for even if there's a.
Then in case of passive thing, in general they can be non-zero. But what funny thing is, I have calculated this thing reducing our model the activity. The particles are spread out, right? Then there is not they are not active. Then it turns out that these values are very low.
Oh, I see.
But I don't know why. But you are correct that as an first saying the formula, okay, we need only probability distribution, yes, kind of. And even if we have some kind of configuration, we can get the probability distribution and we can compute it. Only in our case, what happens only if I take if the Piclet is high enough, then we started to get the non-zero values. But what is exactly how this thing is related to our Piclet and all?
Right, that is
because all these type of quantities so far people have used whatever we have seen in electrical channels, in functional channels, and things like that. But in case of flocking parts, whether we can use it or not, or people have already used it or not, we haven't. So basically, here using the motivation is like you have a focal particle on which you are, and then you have a kind of to think of a trajectory of the particle over time. Okay, so this is your time axis set, and then you have a tube around it, forming by the tube of information, I would say, formed by the neighbors over time. And from this tube, your focal trajectory is getting information all the time. Whoever comes in the tube, he or she become neighbors and give some information. Yes. So there is some. So this is so in case of VCheck also you put it by hand, and in case of if you want to do some experiments, then there might be some. Of course, there should be some areas of this field.
Okay, I think that ends the thing, and let us thank the speaker once again. Sanchari Asya.